Oh, my name is Malcolm Thomas. I'm a building surveyor with over 40 years' experience in construction, property, and estate management. And I've put together a series of webinars to help homeowners understand how the property that they live in or propose to live in is constructed and how to identify the causes of defects and to diagnose lasting remedial repairs. In this first illustration I put up here, I'm demonstrating to you that the typical house has a variety of basic functions, including being weather tight and, of course, structurally sound. It's got to be well insulated and well ventilated and admit as much daylight and sunshine as possible. In this first podcast, I'm dealing with low-rise housing, and I want to introduce you to the basics of understanding structural principles. Before considering alteration works, you've got to understand how the structure is put together, and this has got to commence with understanding the principles that I'm going to demonstrate to you by various illustrations in this presentation. It's aimed to empower and to help you brief a building surveyor, architect or builder, and I've brought to your attention the statement at the foot of this first slide. Where you're planning significant repairs, improvements or extensions, you need to appoint a suitable chartered building surveyor, architect or engineer to help you plan any future repair or alteration work. They will inspect and interpret the structure, how it was built and what condition it's in, and they start with understanding what the load-bearing elements of this structure are. So I'm going to deal in the next 30 minutes with an introduction to foundations, external walls, your roof structure and covering, and internal walls, but from the point of view of a basic sort of structural principles. I'm dealing with low-rise housing, traditional sort of types of construction in masonry and with timber frame, not prefabricated housing. The basic principles apply to old or new properties, single story, maybe up to 4-story in height. And I've illustrated here, the various types of property that you may well possess and live in. Only applies to the UK. You'll have seen on your holidays abroad that a lot of housing, low-rise housing, are constructed with concrete frames or timber frames, but we're dealing with our traditional sort of British forms of construction. To start with, some basic introduction to structural characteristics of materials. Think of a structure as an assembly of materials which is intended to sustain various loads imposed on them, whether they be the load of the material themselves or the fixtures and furnishings in typical homes. All materials and structures, they expand, shrink or deflect, although to greatly varying extents, when they're assembled and loaded in a new building. And we're trying to predict these and other movements and design to mitigate any detrimental effects that they may have. We need the qualities of stiffness and strength in our building materials, and this table here is to illustrate relative stiffness and strengths of different building materials. Compressive strength, on this line that I've indicated here, is the capacity of a material or structure to withstand loads tending to reduce its size, as opposed to those which withstand loads tending to elongate a structure or a material. In other words, compressive strength resists being pushed together, whereas tensile strength resists tension or being pulled apart. And just have a look at the relative values, basically, between timber, concrete, steel, and common brick masonry, which are the building materials that we we commonly use in our forms of construction. Incidentally, the modulus of elasticity there is a quantity that measures an object or a substance's resistance to being deformed elastically when a stress is applied to it. A stiffer material will have a higher elastic modulus. We use a lot of concrete and steel and have done for a long time, and we combine the best characteristics of both of these in reinforced concrete, where we put different steel into the concrete, and then we get the best of the characteristics of both the materials. So, at foundation level, look at this illustration here, and the loads that are being imposed on this external wall. This is a section through a building. It's a solid. Think of it as a solid brick wall, and we've got the wind loading on it, and we've got the various loads of the floor and the roof structure and people living in there. And with the roof, like a book, wants to spread and push away this external wall. So we've got to design it from foundation level such that we're transferring all the loads down through the center line of the foundation to keep that wall nice and vertical throughout the life of the building. So in this second illustration here, the foundation, this is a sort of solid brick foundation resting on ground. It's a very old type of foundation, and as it states, the extra bearing area reduces the stress safely to within the capacity of the soil, because different soils have different abilities to support different loads. So by increasing spreading the load, if you like, you're reducing the stresses on the soil. Note the decreasing thickness of the external wall there through that section as you rise through the building, because of course the lower the building, the greater the loads imposed on the external wall. Bylaws were introduced in this country in the late 19th century, which evolved into the building regulations of today, and you can find these incidentally on a website called the Planning Portal, where it gives you guidance on planning regulations and also the approved documents under the building regulations as well. Over the years, foundations have evolved in different materials, concrete, stone, brick, and the idea is to transfer then safely the loads of the building down to the ground so that the building remains stable. This is an illustration of a modern type of foundation. Well, it's been around for quite a while now, since the 30s, 40s. Cavity wall, there's a section through a cavity wall at ground level, and both those leaves there, the brick facing brickwork on the outside and perhaps blockwork or brick on the inside, bear onto a concrete foundation. Moving on to external walls and the different types that we have, but again thinking of how we construct stable external walls to carry the loads of the building. They've got to remain vertical, and these little sketches here show you how, if the loading on the building is offset from the center line of that external wall, then it could lead to problems with the ultimate stability of that wall. This is meant to illustrate to you that by staggering brick bonding, it makes the wall behave as a cohesive unit and disperses the point loads, for example, from this chap standing on the wall here, evenly down to foundation level. Walls need to be strong and resist instability, overturning, and buckling. So the vertical loaded wall is all in compression, and these little stress diagrams here illustrate the distribution from those vertical loads. And we've also got, of course, horizontal wind loads, thrusting and side thrusting from roof and floor members as well. In our older properties, you'll find the external walls constructed in solid brickwork, and in that close-up here on the right-hand side, you can see the arrangement of the ends and the long dimension of the brick, which is a telltale sign that the house has been constructed with solid brickwork. The individual units being bound together with mortar. Masonry, incidentally, can refer to the common materials of bricks, blockwork, or stone or dressed stone called ashlar. This is a property in London with constructed of typical sort of London stock bricks. Note for now, and I'll come back to it, that of course the brickwork has to be bridged at window and door openings, but we'll come to that in a second. We've been using cavity walls in cavity construction in our external walls since the 1920s and 1930s. How do you distinguish between cavity and solid by looking at the external wall? Well, have a look here at the arrangement of the bricks, and you'll just see the long face of each of the bricks on the face of the wall, which is an indication that you probably will have a cavity wall. We no longer commonly construct anyway in solid brickwork. So stable and strong masonry with discontinuous vertical joints and an interlocking bond make for strong walls, and various types of mortar, a mixture of sand and cement, in some cases lime, have been used over the years to bond our bricks and blocks together. So dealing with the inevitable openings that we need in our external walls, this is a building from the 1950s or the 60s, and we revert to using, for example, a lintel. In this case here, there's a reinforced precast concrete lintel, and you might notice there the cracking. So that's an indication that the reinforcing bars, probably embedded in the concrete, have rusted and corroded, and then that's not terribly healthy, because the load of the masonry above it here bears onto this lintel, which spans the opening to distribute the load to either side of the opening and safely down to foundation level. Lintels could be formed in different materials. For many years now, we've used steel lintels of different profile shapes, and in this photograph that I've just put up, you can see the edge of the lintel, because it's disguised by the facing brickwork there. We don't generally like to see lintels expressed on the outside. In older properties like the Victorian property I showed earlier, you'll find sort of hidden timber bressumas, that were called, or possibly stone beams spanning the openings in order to distribute the loads down to foundation level. Now, another type of construction I'll just briefly show you is a timber frame, where the builder lays a concrete slab, and you have prefabricated timber framed walls, floors, and roof structures delivered to site, erected very quickly, and then an external cladding of different materials applied to, of course, keep the weather out and to complete the construction of the wall. A lot of our 2- and 3-story houses these days are built with timber frame construction, rather than the traditional cavity walls of brick and block. Now, beams, going back to sort of structural principles, I'm demonstrating in these little illustrations here some structural principles of timber floor construction. We like to, lay out floor joists and any roof beams the shortest spanning distance across the walls in our construction, and they're fixed so that they don't twist. Because when you're loading a beam, they tend to deflect, and we've got to understand that and offer some resistance. So the deeper the beam, as a general rule, the sort of wider the span that you can create in your construction. And in this illustration, top right, you can see the relationship between the compressive stresses on this timber beam and the tensile stresses in the lower part of the section through the timber beam. So we've got to design for and allow for these different stresses and deflection that occurs in, let's say, floor joists as a sort of typical example of a beam. Illustrated also, as we see here, with this force representing the loading on the building, causing possible deflections in the structure. We've got to build in and allow for these movements, as indeed the surveyors, architects and engineers do in planning alterations. Moving to roof level, where we may have pitched roofs and flat roofs. The different components of a roof. This is an older roof. Modern roofs tend to be formed in prefabricated timber trusses, which are prefabricated in the factory, but these older roofs were assembled on site with rafters and purlins. This member here supporting the rafters. This is what's called a hip roof, and this is a hip timber here and a ridge timber. All these components sort of built on site and relying on the concept of triangulation to stiffen the roof structure. You'll find various sort of diagonal braces as well, hopefully, underneath, and also in modern truss roof constructions as well. With flat roofs, you've got you may have either a concrete cast slab, or you may get some timber joists or concrete beams spanning between different walls to provide that basic structure upon which you can build a platform and then put your waterproof covering on. Now, amongst the factors that we need to design for is wind loading, and this is to illustrate sections through our pitched roof where we get a wind load, let's say from the left-hand side, and we get a combination of sort of upward and downward pressures on the roof, which we have to allow for in the design of the structure and the roof covering. Make sure that nothing moves too much, and we've got a stable structure. This stability achieved through the cellular interconnection of external walls, internal walls and partitions, and even the chimney acting as a pier as well, combined with the roof structure. The photographs of some properties to show you in the roof space, the arrangement of the purling supported on the hip beam here, the underside of the rafters, compared with this section through a truss roof. It's only a partial view, I'm afraid, because truss roofs tend to be rather cluttered. It's very difficult to take photographs in there, but I hope you can tell the difference between the sort of engineered solution of the roof truss in our properties nowadays, as opposed to the older assembly of rafters and purlins. Internal walls and partitions. In this section here, you can see the arrangement of the internal walls and the external walls taken down to foundation level. In this case, there's a suspended ground floor with some floor joists, timber floor joists. The cutaway shows the floor joists on the upper floor level, cut around the staircase, of course, so that you've got a well there within which you can rise through the staircase and into the loft. This might be a terrace property where you've got purlings spanning between different party walls to provide the basic load-bearing structure for the roof. And in this cutaway, planning various internal alterations with beams and columns behind an existing facade, and you've got to make various allowances for transferring loads so that everything is taken safely down to ground level. Internal walls and partitions, how can you tell if they're load-bearing, part of this load-bearing skeleton structure or not? Well, you could tap them, tap a partition wall, and if it sounds hollow, then it's probably a timber frame with the plasterboard on either side, and it may not take a load. So in this instance here, somebody wanted to remove this wall between the kitchen and this dining room on the other side, and it was a lightweight partition, so they were safely able to remove it and extend through to provide a larger room. It's just an initial indication by tapping on the surface of the wall to see whether it sounds hollow or whether there's the sort of dull thud of possible masonry, brick or block behind that plaster finish. Always rely, of course, on taking professional advice. The first floor in a two-story house will very typically be lightweight partitions, which more often than not will probably won't take any load from the roof. There's a good website I've come across, homebuilding.co.uk, and they've got lots of photographs taken in, is published in March 2020, of different arrangements of transferring loads with beams and columns when you're carrying out internal alterations. The engineer will design these for you to make sure that structural codes are followed, and Part A, I beg your pardon, of the building regulations are complied with in ensuring that the load-bearing structure of the house is maintained after alterations. So, to acknowledge some references that I've used in putting this slideshow together, and finally leaving you with a final reminder that under no circumstances does this information provide or constitute legal advice. Take professional advice from surveyors, architects, or engineers. Thank you for watching, and I'll leave you with this little incident here where they hadn't quite got the loading calculations correct, and something disastrously happened, and they had to incur far greater expense in resolving this issue. Best to take professional advice, get the loading right, understood, and I hope you've learned a little bit more now about structural principles. Thank you.